Hello. In today's topic, we are going to be calculating and constructing what we call probability distributions. We've constructed frequency distributions in the past. That's like a bar graph where each bar represents the count number, but now we're going to be making bar graphs where the size of the bar represents the probability of that event occurring. So to start, just want to review something that we've done in the past. So we calculated the following in a prior discussion, and we're going to use this idea again today. So here is the situation. A company hires you to track the number of minutes visitors spent on their website during a recent session. What was the average number of minutes for each visitor? So just to recall, so the problem with this situation at first was they did a range. So we used the midpoint. So 6 people spent between 7 to 18 minutes. In order to begin to calculate an average, we took the interval and we took its midpoint. So we said 6 people spent 12 and a half minutes on the website, 10 people spent 24 and a half, 13 spent 36 and a half, dot, 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 all the way down. And we wanted to calculate the average. So maybe if you want to recall how we did it, or you want to think through it yourself, pause the video because I'm about to go through how we did this. So how we did it was we said this. We said 6 people spent 12 and a half minutes. So how many minutes would that be? It would be 6 times 12 and a half. 10 people spent 24 and a half minutes. So that'd be 10 times 24 and a half. So that one's 245. I can do that one in my head. So 245 minutes for this one. 13 people spent 36 and a half minutes. So 13 times 36.5. You're seeing all I'm doing as I'm going down, as I'm taking this and I'm multiplying it by the number of visitors. 24 and a half times 10. 36 and a half times 13. And so I'm just going down the chart, multiplying the value by how many people actually did it, the frequency. And I get how many minutes then in total. So all of these are going to be, each of these, the units are minutes. So I calculate all of these values, add them all up, and then divide by the total number of visitors. 6 visitors, 10 visitors, 13, 8, 5, 6, 2. What I end up with is an average of 41.78 minutes spent for each visitor. So I needed to multiply each of these pieces, get the total number of minutes after I summed them, divided by the total number of visitors. So we're going to do that very similar calculation today, not with a frequency distribution, but with a probability distribution. So hold on to that image in your head. Before we start, we need to discuss a few vocab words that are going to get used in this section. One of them is called a random variable. So a random variable represents a numerical value associated with each outcome of a probability distribution denoted by X. So a random variable is essentially something that can happen. There are two types of random variables. There's random variables that are called discrete random variables. That's when they can occur at only whole number values and zero. So it has a finite or countable number of possible outcomes that can be listed. So example, number of sales calls a spokesperson or salesperson makes in one day. That can only be discrete. You can't make 1.5 calls or 3.2 calls. You can only make 0, 1, 2, 3, 4, 5. So discrete meaning individual pieces. The other type of random variable is called a continuous random variable. A continuous random variable has an uncountable number of possible outcomes represented by an interval on the number line. Example might be hours spent on sales calls in one day. You could spend technically 0.3 hours. That'd be 18 minutes. So all the way up to 24 hours, because you can do intervals in between, not just the whole numbers. We would call this a continuous random variable. So the first goal is to be able to decide between the two when given different scenarios. So here's scenario number one. Let's say X represents the number of Fortune 500 companies that lost money in the previous year. Is this discrete or continuous? This one would be discrete. You can only have whole number companies. You can't have, 2.4 companies. You can only have 2 companies or 30 companies or something like that. So that's a discrete scenario. Situation number two, the volume of gasoline in a 21-gallon tank. Obviously, you don't have to just have whole number, values. It's not like your gas tank jumps from 1 to 2. It's got to go in between. That's a continuous situation. Can have any number of gallons between 0 and 21, including non-whole numbers like 11.4 gallons. Once you understand the idea of a random variable, whether it's really discrete or continuous, we're going to look at first discrete, because each discrete random variable has an associated probability with it. For example, e.g., the probability your 21-gallon gas tank will need 15.5 gallons on the next fill. By listing the probability of each random variable in a table or graph, you're making what we call a discrete probability distribution. In a discrete probabilities distribution, what you do is you list each possible value that the random variable could obtain, and then you write its probability next to it. It has to have the following two conditions satisfied. The probability of each event has to be between 0 and 1, and if you add up all the probabilities, they have to equal 1. It's kind of the two rules for probability. If needed, notice this is not in the notes, it's better just to work through an example. The book lists the following steps. If you want to, you can pause the video and read through it. Otherwise, we're just going to do one. So here's the situation. A psychologist administered a personality inventory test for passive-aggressive traits to 150 employees. Individuals were given a score from 1 to 5, where 1 was extremely passive and 5 was extremely aggressive. A score of 3 indicated neither trait. Construct a probability distribution for the random variable x, then graph the distribution using a histogram on the next slide. So what we're going to do is we're going to take a frequency distribution and we're going to construct a probability distribution. You'll notice the left side of the column doesn't change because you can only get scores 1 to 5. What's going to happen is we're going to change these frequencies are counts, into probabilities. So for the first situation, there were 24 people who scored a 1. Well, I need to take 24 divided by 150. So the probability of getting a 1 is equal to 24 divided by 150, which is 0.16. The probability of getting a score of 2, there were 33 people, so this would be 33 divided by 150. Grab my calculator, 33 divided by 150 is going to be 0.22. Probability of getting a 3, well, there were 42 people, which that exhibited neither trait. We learned that's what a 3 means. 42 divided by 150 is 0.28. There were 30 people who's got a score of 4. 30 divided by 150, that's 0.2, that's a fifth. And then there were 21 people who had a very, what do we say, extremely aggressive score. So 21 divided by 150 equals 0.14. Now I have a probability distribution. Now I can say, there's 20% of people who scored a 4, 22% of people that scored a 2. We should verify real quick that we actually made a correct distribution. We verify that by just checking all of these are between 0 and 1. Yes, there's no negatives and there's no probability bigger than 1. And if I add up all of the probabilities, so 0.16 plus 0.22 plus 0.28 plus 0.2 plus 0.14, I get 100%. So it is a valid probability distribution. Now what we're going to do is we're going to construct the histogram for it. So probability of getting a 1 was 16%. So that would be here. Probability of getting a 2 was 22%. It'd be about there. Probability of getting a 3 was 28%. About there. Probability of getting a 4 was 20%, which would be there. Probability of getting a 5 was 14%. Should be right about there. What I see is it's very symmetric, and the average and even the median are looking like they're going to be around the value of 3. That's what the benefit of a histogram shows you. It shows you how the distribution of your data occurred. I'm going to give you a chance to try constructing a probability distribution or constructing a frequency into a probability distribution, and then determine whether it's valid. That is, each probability is between 0 and 1, and they total to 1. So this is the number of sales per day and how many days they had of that. So for example, there were 9 days where they had 4 sales in that day. So give it a chance and come back and see how you did. Okay. The probabilities of the following are 16%, and then 19%, and 15%, and 21, and 9, and 10, and 8, and 2. Because if you actually total these up, you're going to find the total to be 100. So 100%. And yes, it's valid. Each of them are between 0 and 1, and because this was added up to 100 days, they're going to add up to 100%. Besides constructing the distribution for the data, people also care about 1, the average, and 2, the variation of the data. The average we call the mean. The mean of a discrete probability distribution is simply, they use this symbol, it's called a sigma symbol. This right here is called sigma. It means the sum. I need to add up all of the random variables times their probabilities. That's what we did in the warm-up. And then that will give me the average score. So each value of x is multiplied by its corresponding probability, and the products are then added up. This is the Greek symbol sigma, it's used because sigma starts with S and we are summing all of the individual variables times their probabilities. So find the mean score for the personality score and interpret the answer in context. What we're going to do here is calculate each of the individual values. So 1 times 0.16 would be 0.1, and 2 times 0.22, then 3 times 0.28, then 4 times 0.20, then 5 times 0.14. It's what we did right in the beginning with how many visitors visited the websites. I get all of these individual ones, and then I add them up, and then the last part is I have to divide by the total of this column. Before we had to divide by the total number of people that visited. Now we have to divide by the total probability. So I add up all of these individual values. I then end up with 2.94. And I don't need to divide really by the sum of the probabilities because we know it's 1. So if I take 2.94 and divide by 1, I still get 2.94. That's the benefit of calculating the average for a probability distribution, is that last step, dividing by 1, is always going to be there because it's a valid probability distribution. But if you go back to our original warm-up question, the last step we could do was divide by this number, which is the sum of the number of visitors, the sum of the frequency counts. But if my distribution is a probability distribution, then the sum of the probabilities is just going to be 1. So I divide by 1, it's just 2.94. That's the average. Since this score is very close to 3, we would say that the average employee demonstrates neither passive nor aggressive traits, which is what we kind of saw in our graph. You know, the middle is the median, and if it's symmetric, it's going to be very close to the mean. It appears to be right around 3. So average person appears to not have passive or aggressive traits. That's the average. Besides the average, people also care about the variation in the data, measured using either the variance or the standard deviation, although the standard deviation is by far the most common. There are formulas to calculate them, very similar to what we did. We're going to find how far away you are from the mean, multiplied by your probability. Square it, because it could be positive or negative, and then we need to take the square root to undoing the square. You can calculate it by hand if you'd like, but we're just going to rely on technology to do this for us. So it's not really important to write down these formulas. We're going to use the calculator. So this is what you need to do. You need to go to stat and then edit, and you need to enter the values of the discrete random variable x and L1, and then you need to enter the probabilities P of x and L2. So just to show you where you would go to stat and then edit. And then in L1, you would need to list the scores, 1, 2, 3, 4, 5. And L2, you would list their corresponding probabilities just like Step 2 then is you would go to stat, calculate, and then select one variable statistics. Calculate, choose option 1 and hit enter, and this is where the directions differ depending on your calculator. Once you've hit enter for a TI-83, you need to tell it which column you put the variables in, the scores, and which one you put the probabilities in. You would choose option 1. If you have a TI-83, L1, comma L2, because they're right here. So you need to hit second, and then it looks like you're hitting 1, but you're hitting L1. Then you hit comma, then you hit second, and it looks like you're hitting 2, but you hit L2. And where you store those values. For a TI-84, it is the program, the operating system of sorts, asks you where it forces you to answer. It says, in this one, the list is in L1. My frequency list, I would hit second, L2, and then I would hit calculate. Once I've done that, it would give me the following data. And I see here is the mean that I calculated from before, 2.94. And down below, this is my standard deviation, 1.27. We'll call it 1.3. What that means in context is this. So the average score is 2.94, and most of the data values differ from the mean by no more than 1.3. We could also say this, most of the data falls between 1.64 and 4.24. This is how I got that. I know the average score is 2.94, and I know a standard deviation is 1.3. So I went 1.3 above and got 4.24, and then I went 1.3 below by subtracting 1.3, and I got 1.64, and then I know that most of the data then is going to occur in between those two values. That's the benefit of the standard deviation. It gives me a range of values where most of the data is going to occur. And if I go back and look, 1.64 to 4.24, 1.64 would be right here. So 1.64, right in here to 24, I think, something like in here. That's going to capture, the majority of the middle of the data. So that's what we mean by the standard deviation in fairly loose terms. That's the benefit of it. Let's go down here so we can see it. Okay. Another name for the mean is the expected value, as that is the value one would expect to occur on average over many trials. It is written as E of x, so just to be aware, just another vocab word for it. It's a synonym for mean. The expected value is equal to the mean. It's equal to the sum of the discrete random variables times their corresponding probabilities. So we'll do one example of that. It's used a lot in developing like gambling games or things like that, or like odds of raffles. So at a raffle, 1,500 tickets are sold at $2 each for 4 prizes of $500, $250, $150, and $75. You buy 1 ticket. What is the expected value of your gain? Note, gain is equal to prize value minus the cost of the ticket. So each ticket we said costs $2. So there is 1 ticket that's going to get a $500 prize, which means its gain is $498. There is 1 ticket that's going to have a gain of $248. There's 1 ticket that's going to have a gain of $148. There's 1 ticket that's going to have a gain of $73. And there's 1,496 tickets that are going to lose their $2 because they didn't win. And I want to find what's the expected gain for an average ticket. So what do I do? Well, I'm going to calculate each of these. I'm going to take the gain multiplied by the probability. Gain times probability, gain times probability, gain times probability, gain times probability. Add them all up, and that will be my average or expected value. So $498 times 1,500. So I could use colors here. That's this. Then 1,500, or divided by 1,500 times 1 over 1,500. 148 times 1 over 1,500. $73 win, because it's $75, but you paid 2 to play. And then the last one is a $2 loss for $14.96 out of 500. Find the values of each of those, add them up, and I see it's negative 1.35. So this means you can expect to lose on average over many trials $1.35 for each ticket that you buy. That's why it's called gambling. You're expected to be losing. The house should be winning. So if you play this over and over and over and over, on average, you're going to lose $1.35 per play. Be aware, it is actually impossible to lose $1.35 in each individual game. The average does not have to be actually possible. Like, for example, if I asked you what's the average number of kids in a household in the US, it might be 2.2. It's impossible to have 2.2 kids, but it's the average. So just be aware of that. Going to give you a chance to try it, and that'll be it. So find the mean and the standard deviation for the data set and interpret the results in context, similar to how we did with the passive-aggressive trait ones. So the number of defects per batch of camping chairs. So 0 defects occur for 25% of camping chairs. 1 defect occur for about 29.8%. 2 defects occur for 22.9%. 3 defects for 16.8%, all the way down. I would like you to tell me what the average is and the standard deviation and interpret it in context. Pause the video, come back and see how you did. So you should have found the mean is 1.5 and the standard deviation is 1.2. This implies the average batch has 1.5 defects, so between 1 and 2, and most batches differ by the mean from the mean by no more than about 1. You could also say the majority of batches have between 0.3 and 2.7 defects. If you start at 1.5, subtract 1.2, you get to 0.3. If you start at 1.5, add 1.2, you get 2.7. So it's saying the majority of camping chairs are going to have between 0.3 and 2.7 defects. And that is it for today. Thank you very much and have a good day.